So welcome to today's lecture. We're going to do a little bit of something different today. What I want to do today is not talk to you about sort of one of the standard topics we've been covering that are typical to a third year software quality assurance course. Instead, what I want to do is talk to you a little bit about some things that you may not see in a normal undergraduate course, or you may not see in a normal software quality textbook. And what I want to talk to you about is some research that we're doing in my lab, or that we've been doing over a number of years, in the area of advancing test automation using artificial intelligence. This is actually a talk that I gave last year at the International Workshop, an invited talk at Next Day 2021, which is Next Generation of Test Automation. So I'm always happy to stop and answer questions in that. I'm not going to cover everything that's in the talk. I'm going to just try to cover a few key things so that you get some ideas. But love to hear feedback, love to hear questions. The whole idea of this is I want to give you a sense of what research in this area is like and what sort of some of the advanced things that are being developed that might not be in practice yet, but to give you an idea of potential. Also, because machine learning, artificial intelligence is something that, I hear a lot of students expressing interest in, I also thought you might benefit from learning a little bit about the intersection of AI and software testing, software quality, and how AI can actually be used to enhance software quality. Does that sound good? Excellent. So let's get started. So in general, what are we talking about when we're talking about software testing automation, and what are the trends that are around? So there's sort of three general trends that I would say exist right now in the use of automation in software testing. Okay, one of the first trends is with the software itself, and that's namely that when we think about today's software versus software 5 years ago, 10 years ago, 15, and so on, what we're seeing is that software continues to scale up. It continues to become more complex. And what this means is as the software, the scale and complexity of software grows, the size of our test suites also grows. So the scale of our testing grows with it. That makes sense, right? Based on what we've learned about in the course. And as testing scales up, that also has led to a need for more automation of testing tasks in order to manage the testing process. And that means that things that maybe were done manually in the past now require a little bit of automated help. So that's one trend that we're seeing, is this sort of scale and complexity placing more of an emphasis on the need for automation. A second trend that I've observed in this area is agile practices and the growth of agile practices, namely that agile development, whether you subscribe to Kanban, Scrum, XP, or some other methodology, um, it really does emphasize frequent and rapid or even continuous release cycles. And when you do frequent, rapid, or continuous release cycles, you need to be able to release fast, because frequent releases don't work if it takes a day to build the software and test it between releases. So the continuous release cycles of Agile really do also emphasize the need for test automation so that the testing does not become a barrier that impedes the frequency of the release cycle. So we now have larger scale software and we have frequent releases, both putting pressure on the need or amping up the need for automation and testing. The third trend that we're seeing is that the number and distribution of testers on projects is growing. And this is even before the pandemic, where so many people are actually doing this stuff from home. So even like people who used to be in the same office maybe are now distributed across a city. Um, but when you have a large number and a large distribution of testers on a project, there's actually some coordination that happens to happen and some management that has to happen in terms of testing and development activities. And the need for coordination with a distributed team also necessitates the need for more automation. Automation, it's basically, we're seeing the need, all of the needs being maximized here in terms of what they're requiring. And it just isn't feasible as things get more complex, things get more frequent, things get more distributed. We just can't expect people to manually be able to do everything at the same speed and with the same level of quality as they've done in the past. It's not feasible. So all of these trends sort of are pushing us towards more automation. Okay. The second thing that I want to mention is, well, if you believe what I just said, which is that the trends in software testing are pushing us towards automation, the second part of this is that this need for automation of new software testing activities, so automating things that were previously done manually, as well as further optimizing existing test automation. So things like execution of tests, the evaluation of tests in terms of comparing them to expected values, those kinds of things. If you believe that there is a need for these things, well, that need actually has the opportunity to be filled by AI, right? AI can naturally fit this opportunity. So, what do I mean by AI? It's important to know, for us to do this, and I want to just explain this a little bit because some of you may have done a course in machine learning before or artificial intelligence, but that wasn't a prerequisite for this course. So I want to make sure that we all have a good understanding of what I mean by AI. So the first thing is that AI itself is a very evolving concept, right? I actually use the term AI because it's sort of an umbrella term for me because it encapsulates a number of different methods that I'm interested in. But AI as a really as a true meaning of what AI is, it's in terms of artificially intelligent. I typically when I talk about AI, I'm not talking about trying to achieve that. I'm really just talking about the current state of the art techniques that exist in AI and how they can be used to leverage software for automation purposes. So really, what I do is more of a practitioner of AI techniques. So the three categories of things that I'm really interested in as artificial intelligent methods that could be used to leverage for software test automation. The first one is something called meta-heuristic search techniques. And these are things that you wouldn't see in a traditional machine learning course or AI course. You would probably more see them in an algorithms course because they're actually a specific class of search-based algorithm techniques like genetic algorithms that can be used to solve some of the complex problems we have in areas like software engineering. The second category that I'm interested in of techniques is machine learning algorithms. So things like support vector machines, clustering algorithms, random forest, whatever you want to talk about. These are what we more think of as traditional machine learning algorithms. The third category is more what people today think of as the state of the art in AI, which is the neural nets and deep learning algorithms, which are implemented often using neural networks. Any questions about that? Are these concepts new? Any of these concepts new? Are they concepts you've heard of before? Heard of all three or just heard of some? Some are new? Some. Okay. Well, I'll just say a little bit about each of these before I move on. So, in terms of what I mean by machine learning, this is basically an abstraction of how machine learning works, okay? A machine learning algorithm is typically involves training of data, so which is a form of feature. So often you require expertise. When you're doing a machine learning, you as the person creating the machine learning model, you need expertise to be able to understand from the data you have what features, what information that's in that data set is useful to use as features for the machine learning algorithm. And you'll take a certain amount of data, we'll call it the training data, and you'll feed this into your favorite machine learning algorithm, and it will use that training data to produce a model. For example, if we were dealing with a support vector machine, one thing you might do is you would take in a vector of features, and you would take in a label or a classification for each vector. So for every vector of features, you would classify as a yes or a no, let's say. And then your machine learning algorithm will use that information, that labeled training data, and it will use it to create a model that when given a new vector of features will be able to answer yes or no in the same way as your labeled training data. So first you use the training data and the ML algorithm to create a model. Then you take in new data and feed it into the model, and it produces output for that. So that's the just generic approach to how this works. And if you want to think about practically some of the applications of machine learning, um, what you see here is a list of possible methods, and you also see some of the applications. Primarily the stuff that I've done in our research has been in the area of classification and clustering, more so than the regression and optimization. We've done a little bit on prediction, but it's mainly been classification and clustering type of problems. So the idea here is that those tend to be what the problems in software engineering that I tend to work on with students in my lab. So how does that differ from deep learning? Well, deep learning is not typically constrained by the machine learning's limitations with processing raw data. In other words, you have typically a lot more data when you're dealing with deep learning, and it typically, because you have a lot more data, um, it's actually able to do a little bit more things just through the brute force aspect of it than a machine learning algorithm. And what you'll often see here is actually that a deep learning algorithm often has multiple layers. So it has an input layer, an output layer, and a bunch of hidden layers in between. And what it ends up doing is it's actually, when it's going through this, it's actually coming up with inferences and figuring out how to take the input layer and get to the output layer through these multiple layers, okay? And one big difference here between deep learning and machine learning is machine learning doesn't take raw data. What it does is it takes features. So you have this machine learning expert or domain expert who has knowledge, and they actually have to take the raw data, generate the vectors of features, which then are used to train or to be fed into the machine learning algorithm. Let's say, for example, a machine learning algorithm's job is to predict if a picture of a vehicle is a car or a truck, okay? So some of the things that it may actually use as features, if we were doing a machine learning algorithm, we may use things such as the number of windows, if it's a side-on view, right? We may also use a ratio of the length of the vehicle to the height of the vehicle, or the height, the size of the tires in ratio to their span, or we may use information if, for example, trucks had certain colors versus cars, we would use that. But you would have to define all those features in a machine learning algorithm, calculate them, and feed them into the algorithm to predict. So you wouldn't be passing in raw images, you would be passing in a vector of features of those images, right? Now, with deep learning, you don't have to identify the features. The deep learning algorithm will infer those features for you. So what it does is it takes in as input the raw images of vehicles, cars, trucks, whatever, and it tries to come up with a classification from the raw data. So it no longer requires the expertise of the person who's trying to create the model. This can be powerful as well as dangerous, because what it also means, while it means that it makes it more accessible to a lot of people, so you don't need to have the machine learning expertise and knowledge, it also means that you're throwing a lot of data at a problem. You don't always know why a certain I guess, output is being achieved. It's sometimes hard to understand that, which means that it's sometimes hard to understand when there's bias in your data and so on. For example, if it just so happened that all the car pictures I gave were red and all the truck pictures were blue and green, it may be that it's just using that information. And the next time I give it a red truck, it'll think it's a car, right? Not a bit with a car and truck, but if the picture was instead a picture um, say, some sort of medical scan and you were trying to detect tumors, you may be a lot more concerned about how it's reaching its result, especially if it says negative or positive, which have significant risks associated with an incorrect prediction. Okay, so I'm just trying to get through some of these intros, and then I'm going to give you an example. Um, So this is actually a quote from David Parnas, who's a very famous software engineering researcher. And he basically said, learning is not magic. So this is something where people sometimes get so excited about machine learning and AI. The reality is, I don't really worry about these things and whether or not they're going to be intelligent. I'm really more interested in the practicality of it. And if you think about it from a very pragmatic perspective, learning algorithms are not magic. Learning algorithms are actually just using data that's collected to improve future performance, right? So that's really what it is. It's using it statistically, it's using it logically, whatever underlying techniques are in the model or the approach. It's using some collection of data to improve future performance. That's sort of the end goal. And with this understanding now of AI, how can AI be applied to software testing? Well, there are several ways that we've been doing it in the lab and that has been done in the literature. The very first way is through what's called automation. So automation is the idea that we take existing testing activities, including the creation of software artifacts, i.e. creation of test cases, and we automate it. So we no longer manually create test cases like you did in phase one. We take the requirements document, we break it apart into a set of requirements, feed it uh, into an algorithm to build a model, and then we use that to predict tests automatically from them. Or it can also be used, instead of automation, it can be used for what's called recommendation. And this is a little bit different, where you're not trying to automate tasks that are currently done either manually or done in some other more primitive automatic way, but instead you're trying to assist software testers to improve their performance. For example, rather than just managing when tests are retired automatically, you could instead have a recommendation tool which sort of flags potential tests that could be getting close to end of life for a tester to then look at and make a decision on whether they should be retired or not. So you're doing a recommendation, not actually automating the task itself. So you're actually helping testers to do their job better, not replacing their job with automation. And one of the keys when you're doing any of these things is that if you want to try to address a software development problem using artificial intelligence, you need to reframe it in terms of the terminology of that method. For example, we heard the term classification, right? Or prediction or optimization. Well, guess what? If I can frame something as a classification problem, then I can address it using a machine learning algorithm. So that is just one example of something. And I'll show you one example of that in a second. But first, the sort of like a piece of information for you is that in general, easy tasks or problems, so things that are sort of easy for testers to do that they do frequently, these are really ripe for full automation, right? Because typically you can do them, if they're relatively easy to do, it's probably something that can be automated. And it probably means that it's probably something the developer or the tester might be in favor of automating so they can focus on more challenging and interesting problems. Um, but when you're on the other end of the spectrum, when you're talking about the really hard problems that a developer or a tester has to solve, they may appreciate some recommendation-based solutions there. They may appreciate some help. And the way we do that often is through what's called human-in-the-loop approaches. That's approaches where we don't do full automation, but instead we make recommendations which the user or the tester ends up improving or deciding on and how to proceed, and then we continue on from there. So it's this continuous loop with suggestions by the algorithm, actions by the testers, recommendations by the algorithm, actions by the tester, and so on. So that's a little bit in general. That's a bit of a high-level overview of the AI and how it can work in software testing. What I want to do now is give some specific examples to things we're doing um, or we've been doing in the lab. Are there any questions, though, before we proceed? Is this interesting to people, or is it sort of way over your head? Okay. One person said interesting, a little over my head, interesting. Okay. Okay, so I'm hearing that it's interesting, maybe a little over the head. It is interesting. Okay, cool. And like, look, this is why I said, and if you're feeling it's a little over your head, don't worry about it, because like I'm not really, this isn't what I'm gonna like, I'm not gonna go into deep detail about this on the test. Um, that's not my expectation here. Um, to be honest, this slide right here is probably the one that I would, if I'm going to ask you anything from this, I'll ask you, it would be this slide right here, asking you how can you apply AI to software testing, which is through automation and through recommendation. Like that's the kind of level of something I might ask you if I asked you anything from these slides. That was a big hint, just so you might want to write that down. Okay. Okay, cool. So what I want to do next is I want to actually tell you briefly about some of the very early work that I did that we were doing in the lab on this topic. And this first example is actually about predicting mutation testing scores using source code and test metrics. So we've already covered mutation testing, right? And we learned that mutation testing works by taking a program that you assume to be correct. It's sort of a meta technique. And what you do is you create a whole bunch of variations of it, each with a single mutation. And what you do is you can then assess your test suite to see if it's actually able to detect all of those mutant programs by actually seeing if the output for the mutant programs is different than the output for the non-mutant original program. And this is a way to assess our test suite, right? A high mutation score means we have a very solid test suite. A lower score means that there are sections of the program or types of bugs that our tests simply aren't catching. So we maybe need to add tests. So one of the challenges that's always existed with mutation testing is that it is very costly, right? So you have to essentially run your testing with every variation, with every mutant. And if you have hundreds or thousands of mutants, this can be expensive. So there's been a lot of work on what we call optimization of the mutation testing problem. So some people have come up with what they call do fewer approach, where they've learned that, hey, we don't need to use all the different types of mutations available or mutation operators. Instead, it turns out that there's a subset of them called selective mutation, which if you can provide coverage of those with your tests, then that's a good indicator that you provide coverage of the larger set. There's also a do smarter approach, where what you're trying to do is actually find out if a mutant is killed earlier. So what you're doing is, rather, for example, than waiting till the program ends and comparing its outputs, let's actually compare intermediate values right after the mutant code is executed and see if internally variables are of different values or not. So you check sort of in the middle point. Another thing is what's called do faster, where you do things like parallel execution. So you actually are executing multiple mutants at the same time so that you get the results for all of them sooner. This doesn't save processing time, it just parallelizes it, so it's in real time, it works faster. So in general, though, all of these techniques are really because mutation is often done iteratively. So the idea here with mutation is often I have an existing test suite. I want to add a new test to it, or I want to improve it. So what I do is I add a new test, I mutation test it to see if it improves my mutation score. So if I add the new test, do I get a better score a higher score than I did with the previous, when I just had the previous existing test. And I can iteratively do this until I get a really high score. And this is a way to improve iteratively your test suite. Does this make sense? Because we talked about this when we did mutation testing, if you recall. Any questions about this? Okay. So what we actually did was we actually, in this case, used machine learning to do this. So the idea is that if we're doing this iteratively, it's really expensive to do the testing every time. So what about if instead of doing the testing every time in this loop, what about if instead we only did it, say, every 5 iterations, we did the real testing. And in between, whenever we wanted to add a new test, we had a machine learning algorithm which will just analyze the code and the tests and tell us, hey, this test this will improve your score, or this will be, it'll predict that the score will be higher. So the idea is, could we actually use machine learning to cut out some of the actual testing to improve and optimize the time it takes to do iterative mutation testing? That was our goal. And the way we did the data collection is that in order for us to assess if a given test suite, what its mutation score will be with a given code, we actually need to collect metrics on 2 different things: on the tests themselves, on the source code. Okay? And what that means is, it means that we need ways of actually gathering metrics. Because remember, we're going to use machine learning here. So we're not just going to throw the raw data at a deep learning algorithm. We did this actually over 10 years ago originally. And this was actually won a Best Paper Award and was the first paper that actually did machine learning based mutation testing. So what we did was we used a number of metrics plugins. Remember, we just covered metrics. To actually get information about the test and the source code, which we could then use to train our algorithm on. So in our case, if you look sort of at the bottom down here, what you can see, let me just sort of turn this way. You see how it's green bar and the blue, right? At the very bottom. The green is our feature vector, and the blue is the category we're trying to predict. So what we want to do is for a given set of tests, because every set of tests, different set of tests, is one instance we're checking, right? So we're checking different test suites. So we take one set of tests, we generate the metrics for those tests and the corresponding source code, and that gives us our vector of features. And the mutation score that unit tests actually achieve with that source code, that is actually the value we're training on. So what we're seeing here is that we actually are going to use some initial mutation testing that we do normally manually early in the iterative process. We're going to use this to train the algorithm so we can predict later. And the types of information we collect here for features, one of them is we collect coverage metrics, so things like statement and branch coverage for our tests with our source code. We also collect source code metrics of both the tests and the source code. So we know things like the complexity of the code, how long it is, that kind of thing. And then we also collect the mutation score for our set of tests with our source code. And you can see in that data collection box here some of the different tools we use for that. But that's not really super critical. And once we do this, this allows us to build our model. So once we have a model, we can now do prediction, right? We can now predict the mutation score for a given set of tests. And we think of this as do fewer and smarter approach. Because on one hand, we're doing fewer manual test iterations, but we're also trying to do it smarter in that we're trying to, for the test iterations that use machine learning, we're trying to optimize it so it's faster than doing it manually. So, and at the time, we weren't able to predict to the like 90%, 91%, 92%. We were predicting it in 3 general categories: low, medium, and high. So a low mutation score, a medium mutation score, and a high one. Future work since this has actually sort of extended this by using larger amounts of data, faster machines to do this at a more fine grain. So what we basically do is at any point, once we have our model and we have a new set of unit tests, say we add one to it and we have our code, we can then collect the exact information we did before when we were training. We collect that information and that becomes our feature data. We then feed that into our machine learning algorithm and it will predict the mutation score for us, which will be the score for those tests with that source code. And we actually did analyze this on 8 open source Java projects. So we analyzed this on approximately just under 130,000 lines of source code. We did unit testing at both the method and class level. So we did it. It was over 1,600 classes, over 13,000 methods, with over 10,000 unit tests that we included. We didn't have to write any of these unit tests, so we limited it to Java projects that had existing unit tests that we could actually evaluate, because we didn't want to bias any of our evaluation by having us create any of the data we were analyzing. Okay, and what did we find? Well, we found that this was actually promising as a technique. So for method level mutation, meaning doing units at the method level, we were able to achieve a prediction accuracy of about 23.5% better than random. So that means random, so that wasn't too bad for us. We were actually quite happy with that. So we were able to find that it was better. However, the lessons we learned about this was that the class level mutation was actually a much harder problem than the method level, mainly because we were using a lot of source metrics that gave us insight into a given method's code complexity in that. But when we went to classes, there weren't really good metrics for class level source code. Instead, what we were doing was we were actually trying to figure out, should we be using the average of the metrics for all the methods, the min, the max of those, the median, and what we found was trying to do that wasn't as effective. The other thing we found was we tried to do prediction both within a project and across projects. And doing it across projects was actually way harder as well. So this is sort of one of the big challenges. That's one example. Any questions about that example? Okay, I'll assume that I just explained it in a way that people understood, or maybe you're still processing. I'll try to end it in about 10 minutes so that you have 10 minutes at the end to ask any questions and we can have a discussion if people are interested. So the second example that I want to talk about is one from ICSE 2020. And this is actually a paper that my current master's student, Jude, did, his work. And I want to point this out because Jude's work was actually his undergrad honors thesis, and it was published in the International Conference on Software Engineering, the premier conference in the world for software engineering research, as a new ideas early research track, which is basically for late breaking results. So he actually published this, and it was actually really well received, in my opinion. And you can actually, just like with all of our work, we actually open source all of it. So you can go to the URL and download it, the code, you can get his data and everything. So what Jude was doing was, we were also doing an automation, but we were actually automating something that isn't quite a testing activity, but it's an activity that's relevant to testing and specifically relevant to bug fixing. So one of the things that happens is when you have software that's been deployed, you might have seen sometimes when your software system crashes, it asks, do you want to send a bug report or do you want to send the log data for the crash to the developer? Have you ever seen that sort of show up on your screen? Yeah, and when that gets sent, that sometimes can be utilized as a way to identify a bug. And if there's a bug related to that, that will usually be used to generate a bug report. So bug reports are a way that bugs get documented for being fixed during software maintenance. And most times when bugs get reported, they actually have to get triaged. So this is the exact same thing as if you go into the emergency room. One of the first things, you'll see a nurse almost immediately, right? And the nurse will assess you, take your vitals, and then tell you to go have a seat. And at that point, and everybody pretty much sees the nurse in the same order, right? But at that point, they triage. So if somebody comes in complaining of severe chest pain, which could be a sign of a heart attack, that person will probably get seen faster than if you've went in with a sprained ankle, right? Just simply because they've assessed that the person with the potential heart attack maybe can't wait to be seen, whereas your ankle isn't going to get any worse by waiting 3 hours, for example, right? And that's a triage system so that the most needed, the people with the most serious injuries or afflictions or conditions are seen first. Well, with bug reports, it's the same thing. There are so many bugs reports that come in that it's almost impossible just to fix them all in order. So what happens is they are given severity ratings for how critical they are, and the severity ratings help to decide which bugs get fixed first. So let's take an example here. How many of you use the browser Firefox? Anyone use Firefox or has used Firefox? Sometimes, rarely, not anymore. Used it for a time. Only when Chrome has issues, LOL. Only to access my camp. Okay, so there's a whole bunch of reasons why you may or may not use it. But in any case, this is actually from Bugzilla, which is the bug reporting tool that Mozilla uses, Mozilla being the open source foundation that develops Firefox. And this is actually a real bug report. And what I want to point out to you here is that this bug report includes a severity, and you can see the severity for this particular bug is trivial. And bug severity is, quote, the impact a bug has on the successful execution of the software system. So this bug has been deemed to be trivial, meaning it's not a big deal, it's not going to cause major impact. And it's actually, this bug isn't about somebody getting an error or your software crashing. If you read the description or the title, it's end user rights, reads like a protest sign, should be end dash user rights. And if you go down and read the description, what they're basically talking about here is that if you go to open up Firefox and you go to the About Firefox dialog, right, it shows you a whole bunch of information, and it includes a end user rights dialog or block down below. And the point they're making is that end user rights, while it's indicated to talk about what the rights of the end user are, it sounds like you're advocating for ending users' rights, as in advocating that users should not have any rights when using your software. And so this is really a wording thing. It's not actually a bug that will affect how the software behaves, but it is a bug in that it is content in the application which may not actually be understood properly. So this would be something that would be an example of a trivial bug. Does that make sense? Cool. So what we were interested in doing was we were interested in looking at the challenge of automatically triaging bugs. Okay, because a lot of bugs come in, and the bugs that come in, somebody has to have domain expertise and knowledge of the software system to know, is this a really critical bug? Is this a moderate bug? Is it a minor bug, or is it trivial, right? So what we were interested in was this idea. And so it turns out that there are existing approaches to doing this, okay? So this is an example here. So one of the automated approaches that has been developed in the past uses natural language processing in the presence of keywords in bug reports. So look at the example here. The yellow is what we train on, the green is what we predict on, okay? So you take a bunch of existing bug reports that all have been rated with a severity, and you train on those by building a classifier which, using keywords in those reports, the keywords, the presence or absence of certain keywords are the features, And the classification is the severity you're assigning it. So the yellows all have a severity assigned manually that you can use to train, and then you predict on the green one, okay? And this work actually used a data set from NASA, which we also used in our research. And what it did was, which was interesting, is it took this NASA data set, which had projects that had been anonymized. So they were projects just listed as A, B, C, D, and so on. And then it looked for keywords. So for example, things like the word crash, right? So that would be, or catastrophic, or whatever the words might be. So it wasn't the words like the and a and that kind of thing, but it was specific words. Now, what they found was that this was very effective when done within the same project. So if they took project A, they trained on 70 to 90% of that project's bug reports, they could actually predict relatively well the remaining 30 to 10%. Okay? Make sense? Great. However, there's a couple of problems with this, and it's not, and when I say problems, I don't mean that there's something flawed in their approach, because just like anything, this is a starting point, right? This is, this paper answers the really interesting question of, is it possible to predict bug reports using natural language processing data like keywords? The answer is yes. But if you want to go from this approach to something that can be used in practice, you need to be able to do a few more things. One of the things is you need to be able to predict bugs earlier, right? Because right here, you basically have to wait till you have at least 70% of your bug reports manually classified before you can start predicting the severity of bug reports. But when is it you have the least amount of domain knowledge, the least amount of system knowledge to be able to predict bug reports? It's actually early, not late, right? Typically. So there's a problem here in that this actually, because of the training, the fact that you train on the same project that you actually predict on, you can't predict till really late in the process. So the usefulness of this, or the utility of this for a real development team, is limited because of how late you have to do that. The other challenge is that the presence of keywords is problematic, because the keywords are often project specific, right? Even at a place like NASA, not every software system is the same, right? One software system might be um, guidance system for a rocket. Another one might be something about satellite telemetry. Another one might be the communication system that's used in mission control, right? One of them might be software used on the Mars rover. All of these systems are going to have different contexts, different keywords associated with severe bugs, moderate, and so on. So the keywords do not actually allow you to train on other projects and predict on future projects. So it basically restricts you to only being able to do your training and your prediction in the same project. Does that make sense? Have I explained sort of the limits of this well? Okay. So what we did was we basically just, when Jude and I were talking, we were, well, okay, a practical solution to predicting a bug report severity must be effective early in the development process, ideally from the first occurrence of a bug, right? Which means, and what does that mean? If I want to predict from the first bug report, that means I need to either have something that doesn't require training, or it means I have to have an algorithm that is trained on historical data, i.e. other projects. But we already know that keywords don't work for training of other projects. So we started with the task of, how do we train on past projects without using keywords? The solution we came up with was to, rather than look for the presence of specific content like a keyword, we instead were going to look at how the reports were written. namely to see if when somebody wrote a report that's severe, do they write it differently than when they write a report that's trivial, right? Is the sentence structure, the length, the composition, how is this stuff different? So what we did was we actually utilized this. I'll show you our approach. We actually decided to use an existing tool called Doctevec, which builds on top of Word2Vec. It's a natural language processing tool. And what it does is Word2Vec takes a word and gives you a vector of features about it. Doctevec actually takes a document. Sorry, no, yeah. Doctevec takes a document, it's like a paragraph, and it gives you a vector of features about that paragraph. So instead, what we did was rather than use the same project, we took the past project bug reports, fed it into Doctevec to get feature vectors for each of those bug reports. Okay. And we also had the past bug report severity for all of those. So we used the feature vectors generated from Doctevec in combination with the classification of severity. We fed that into a classifier, MLP, to build our model. And then we started a new project. We actually could feed from day one those project bug reports into Doctevec to generate our feature vector, throw that into a classifier, and it would predict a bug severity for us. So by moving away from keywords, which was project specific, we were able to use the Doctevec feature vector, which were more project agnostic. And because we were still within the same organization, which had a culture of how they actually do bug reports, and because of the nature of the type of software they did, there was more consistency in how they did things. We actually were able to come up with a method that could accurately predict bug severity. And what we found was, I don't know why this is jumping. None of that that's really super weird. I wasn't actually touching anything, it was just going. So let me just go back. I've got like 2 slides left, so we're almost done here. So what we did was we took the NASA data set, and you can see the data set here. And this data set they looked at had 5 projects. You can see for each project the distribution of severity ratings in each of the projects A, B, C, D, E. So you can see that they're not exactly the same. And then what we did was, so that's what we had. We had these projects, and each of these bug reports included a whole bunch this type of information. But what we really focused on was the description. That's what we analyzed here, the description of the bug reports. Okay. And what we did was we evaluated our approach versus Severus, which was the keyword-based approach, to see how well it did. And we also reproduced their results to verify that they were accurate. So I'm going to skip the performance measures and stuff a little bit due to time. But what I want to show you is basically this. The blue is Severus, okay? And so remember, when it's as a blue of, say, 50% in A, accuracy F measure, okay? That means that when they trained on at least 70% of Project A, they were able to accurately predict the severity of 50% of the remaining 30% of the reports. When you see the orange bar for one of these projects, it means we were able to predict accuracy of F measure for that project from report number 1. Okay? So we're able to predict the 70% that they required for training as well. And the thing that's interesting is that our method was as effective at predicting bugs, in fact, more effective for 3 of the 5 sets. And the reason it was actually less than some of the others has to do with a challenge, which is the distribution. Is our main hypothesis, because if you remember, A had a different distribution than the others. It had a lot of bug report, particular severity, that none of the other ones had. So therefore, there was really very little historic data which we could use to help us predict that. Okay, so that was a limit for us. So if instead, for example, for A, if we had taken the first 20% of project A, in addition to the historic projects, we probably would have gotten a much higher result. Does that make sense? Or we think we would have, I should say. We also looked at the variation of this with different combinations of historic data using one of the past projects, two of the past projects, three, and so on. And that's the other thing that's mentioned here. Pits C and D are can be challenging too, because if your training data is not representative of the test data in terms of its distribution and that of severities, it's not going to do a good job. And we found that in some of these cases that was a problem. So in conclusion, what we were able to do was we actually were able to present a new method to characterize past projects bug reports without using any project-specific classifiers, any domain-specific classifiers, and we were able to do this by relying solely on historic bug reports and their semantic similarity with the new project. So that's sort of the I guess the crux of what we did here. Are there any questions?